acid number 1 then becomes the starting step in the second part. Okay, so I hope that seems okay. So to say it again, so HSO4 was 10th molar after the first step, and so it's going to be HSO4 again when it's going to break down, and the hydrogen ion concentration is 10th molar, no sulfate yet. Okay, now if you look at the small size of the K sub A2, 1.2 times 10 minus 2 means it's a weak acid, so the system is favored to the left. That's why the completion step is the same as the start step. Now, you can't have a zero in an equilibrium system, so now we have a change step. So we're going to lose some hydrogen carbonate, minus X, and plus X will be the gain of the other two. So at equilibrium, we're going to have 0.1 minus X, X, and X. Plug these into the mass action expression, and you're going to love the math on this. First of all, notice the red X's. You can ignore those. And notice in green I marked the 0.1s. They cancel out. How cool is this? So X equals the K sub A 2, 1.2 times 10 to minus 2. Okay, we're now ready to answer all the questions I want. First of all, what's the hydrogen ion concentration? Well, it was 10th molar after step 1, but after step 2, it's 10th molar plus X. Okay, so it'd be 0.1 plus the 1.2 times 10 to minus 2, so it's 0.112. That's the hydrogen ion concentration. If I take minus the log of that, so 0.112 log change sign, I get a pH of, I'm getting 0.95. Are you also?
Yes.
Yeah, so change that on the thing. That's a mistake. It should be 0.95. Okay, now, what about the sulfuric acid molecules themselves? Notice they were all used up in that first step. Okay, so notice here, there's none at all. So no molecule of sulfuric acid in the system. Now, the hydrogen carbonate is going to be 0.1 minus X. So that's going to be 0.1 minus the 1.2. So I'll try that on my calculator. So 0.1 minus 0.012.
Why was the other one 0, Professor? The one before?
Why is the sulfuric acid this one here?
Yeah, is it just because it's breaking up?
Because notice on very step 1, it broke up 100%. You lose all the molecules. So look over here. So it was 10th molar to begin with. It was 10th molar. We used up all 10th molar. So it's 0.
Okay, thank you.
Okay, now what about the sulfate concentration, SO4 negative 2? This is kind of cool. Okay, it's equal to X, and X happened to be the 1.2 times 10 to the minus 2 molar. Okay, now I'd like to show you a more typical polyprotic acid. Okay, carbonic acid. Now notice in the case of carbonic acid that it has 2 acid hydrogens, but they both have small K sub A's. Okay, so you got a K sub A1 and a K sub A2. Again, K sub A1 is going to govern the first acid hydrogen coming off. K sub A2 will govern the second one. Okay, so let's look at the chemistry, the first step in carbonic acid. So you want to knock off the first acid hydrogen, and what are you going to be left with? Hydrogen carbonate. Okay. Now, notice I wrote start and completion step together. Why? Because of the small k, in the completion step, it's favored to the left. Okay. Now, you can't have zeros in an equilibrium system. That's why you have a change step occurring. So minus X plus X plus X. Okay, and here's your summation line. So at equilibrium, the concentration of molecules is 1 minus X. Hydrogen is X. Hydrogen carbonate would be X. Okay, so we want to solve for X. How do we do it? Plug into the mass action expression. So products over reactant. We'll ignore this X here that I marked in red. Okay, makes the math really easy. Okay, so X squared should be equal to K sub A. So I'll try this on my calculator. 4.3 E7 minus square root. And sure enough, I get an answer of 6.55 times 10 to the minus 4. I'll round it off, 5.7, I'll round it off to 6.56. So that is the value of X. Now, as you saw in the first acid when I showed you, the ending on step 1 becomes the beginning on step number 2. So I'll draw some yellow lines. Okay, so the hydrogen carbonate ended up being X. So this is the hydrogen carbonate. And same thing on the hydrogen ions. They ended up being X. So they're going to start being X here. And there's no carbonate yet. Now, the reason I wrote this as the completion step also is the small k, 10 to the minus 11, means that it's favored to the left. Okay, now this 0 should bother you. So the change step is we're now going to lose, we're going to move to the right. Now we're going to use a different variable. So now it's going to be a loss of y, a gain of y, and a gain of y. So what do we have at equilibrium? The hydrogen carbonate is x minus y, the hydrogen is x plus y, and the carbonate is y. I think it might be useful to solve for y, don't you think? So let's plug into the mass axis expression. So here's hydrogen concentration, carbonate concentration divided by hydrogen carbonate. Now the math is really simple. First of all, we can assume y's are small, so the red line represents we're going to ignore it, and cancel out the x's. Y is equal to the k sub a2, so it's equal to 5.6 times 10 to the minus 11. Okay, we're now ready to answer we're going to answer everything that's in the system. Okay, so the hydrogen concentration, look at the very bottom, is x plus y. Okay, so x is 6.56 at 10 to the minus 4. I tried to add a y to it, it didn't even show up my calculator, so hydrogen concentration 6.56 times 10 to the minus 4. Okay, so let's see, 6.56 A4 minus, I'll store that in memory 1. Okay, and I'll take minus the log of that. So log button, change the sign, I get a pH of 3.18. Okay, what about the concentration of H2SO4? Okay, it's right here. It's 1 minus X. X is so small it hardly showed up my calculator, so it's about 1 molar. Actually, I want to find out what it is exactly. So it'd be 1 minus, we call X. An answer of 0.99934 times 10 minus 1. So it rounds off almost to 1. Now, how about the hydrogen carbonate? What is its concentration? That would be right here. It'd be X minus Y. Okay. So I subtracted Y from X. It hardly did show up my calculator. So it's just 6.56 times minus 4. And what's the final concentration of carbonate? It'll be Y. And Y is the 5.6 times 10 minus 11. So what I always thought was really cool, this is a pretty complicated system, and yet we are able on paper to figure out the concentration of all the species in the system. So really a very powerful tool to be able to do that. And even though it's a lot of math, it really isn't that hard in a way if you take it step by step. By the way, I have a homework problem for you on this also, but I don't want to show it to you yet. So remind me at the end of the lesson to show you the homework problem. It has to do with a 3-acid polyprotic acid. Okay, next. Okay, I want to go over some general rules on manipulating equilibrium constants. Now, you've already seen number 1 before, and that is, if you know the constant in the forward direction, in other words, A going to B is K, what happens if you reverse the reaction? It's B going to A. Well, we proved this to you earlier. All you do is flip over the K. It'd be 1 over K. Now, the reason this is very valuable is sometimes you know the K in one direction and you don't know in the other direction, but if you can figure it out in one, if you flip over the reaction, just flip over the K. Okay, now here's a new one. We haven't seen this before. What happens if you want to add 2 reactions together? For example, we have A goes to B, and we have the reaction B goes to C. Now, you know from Hess's law, you can add these together and get the overall reaction A goes to C. The jackpot question is, what do you do to their Ks to get K3? What's the relationship between K1 and K2 and K3? Now, you might recall from thermodynamics, if these were delta H's, that would be Hess's law. So delta H1 plus delta H2 would give you delta H3. The question is the same thing on Ks? Let's find out. So look over here. I've written the mass axis expression for K1. It's B over A. I've written the same thing for K2. It's C over B. Now, you know the answer for K3, it's C over A. Okay, math fans, what do you have to do to K1 and K2 to get K3? Let me give you a moment to look at that. I'm open for suggestions. Is it going to work to add the two together?
No.
Multiply it.
You multiply and
Somebody said
cancel.
multiply. I'm going to write a little multiply sign. I think that'll work because if I multiply these together, notice the B's cancel out, and you get A over C. So that's exactly right. The right answer in this blank here, why don't you write in your notes? So K3 is K1 times K2. I'd now like to show you a very interesting application of what we've learned here. I want you to see if you can follow the logic in here, what I'm going to explain to you, but don't worry about memorizing anything. That's not the goal. It's just to see if it makes sense. Okay, so I've written down the K sub B reaction for ammonia. So ammonia plus water gives you ammonium hydroxide. Now, you might recall that the K for this kind of reaction is called a K sub B reaction. So it's labeled as the K sub B of ammonia, ammonia and water. Now, a couple years ago, a chemist thought he knew what controlled this reaction, the steps. He said we thought what happened with step 1, which is water breaks up to give you hydrogen hydroxide. Okay, he thought that's what the water does. And the K for that you recognize as the K sub W. Then he thought the hydrogen that's formed in step 1 then attacks the ammonia to form ammonium. Now notice, by the way, if you add these two together, it does give you the right overall reaction. Now, what is the K for reaction number 2? It's really not recognizable except if you look at the reverse reaction. When a chemical gives you acid, that's called a K sub A reaction. But why did Berg write down 1 over K sub A? Because the reverse reaction is K sub A, so the forward must be 1 over K sub A. Okay, now, what is K sub B ammonia going to be equal to? It's going to be multiplying these two together, K sub W times 1 over K sub A. Now, if you rearrange these algebraically, K sub W equals K sub A times K sub B. Now, the whole reason I did this is I wanted you to come up with this wild statement here. It seems to me in science, whenever you get a very simple statement, it must be one of those wonderful truths. So isn't it kind of cool that K sub A times K sub B equals K sub W? Very simple statement, and yet we're going to use this an awful lot. Okay, so again, if you didn't follow the logic behind this exactly, the main thing is to know this conclusion, but I hope I give you enough background so the conclusion does make sense. Okay, so ready for the next slide? We're now going to utilize this.